Welcome to our final lecture in Math 1342, Elementary Statistics at Dallas College, specifically using ALEKS. We're going to be looking at the hypothesis test for our population proportion, which is section 8.4, and 8.5, which is determining which method to use. This is just something that I do in the classroom setting, trying to increase critical thinking in students. And so I have some puzzles, some brain teasers. A lot of it's about math, a lot of it's about how you organize information, etc. Often these problems are straightforward, but they're confusing in the wording or confusing in how we kind of think it through. If Rima is the 50th fastest and also the 50th slowest runner in her school, how many students are there in school? If you want, you can hit pause for a while and see if you can answer these three. So there's 50 people above her. No, that's not true. She's the 50th fastest. So she's number 50. So there's 49 people above her. And she's the 50th slowest. So that means there's 49 people below her as well. So including her, that would be 98, plus her would be 99 students total. Okay, remember she's the 50th, so there's 49 above her, 49 below her, and so she's directly in the middle of 99 students. What do Alexander the Great and Winnie the Pooh have in common? A lot of times we look for more detailed answers in how we organize information, and it's hard to figure it out. This one is really just a semantic thing. They both share the middle name of the. Alexander the Great, Winnie the Pooh. Turn me on my side and I am everything. Cut me in half and I am nothing. Again, it doesn't give you a lot of information. Cut me in half and I am nothing. What is nothing in math? Nothing in math is maybe 0. So if you have 0 on top of 0, notice that makes a number 8. So if you cut it in half, you're nothing. And if you turn it on your side, you get infinity, which is everything, sort of. Okay. All right. Anyway, it's just something I do in class to, again, build critical thinking and really thinking skills, how to take action when you're not sure exactly what to do. So we're going to test a hypothesis about a proportion using the p-value method and also using the critical value. So let's look at an example to introduce this topic. Can virtual reality be used to enhance education? In a recent survey of teachers conducted by Samsung, 85% of them stated that using virtual reality in the classroom would have a positive effect. One specialist believes that the percentage has now increased to more than 90% since virtual reality equipment has become more available. She samples 500 teachers and finds that 471 of them believe that virtual reality would have a positive effect. Can she conclude that the proportion of teachers who believe that virtual reality would have a positive effect is greater than 90%? This is an example of a problem that calls for a hypothesis test about a population proportion. P is the population proportion of individuals who are in a specified category. P sub 0 is the null proportion. X is the number of individuals in the sample who are in the specified category. N is the sample size. And p hat is the sample proportion of individuals who are in the specified category. P hat is defined as the number in the category X over the total number in the sample. Again, none of this should be really new. We've gone through this in different ways before for different testing. The method for performing a hypothesis test about a population proportion requires that the sampling distribution be approximately normal, and these are the following assumptions that we have to make sure before we begin. We have a simple random sample. The population is at least 20 times as large as the sample. The items in the population are divided into 2 categories, and the values, the sample size times the null proportion, and the sample size times 1 minus the null proportion are both at least 10, greater than or equal to 10. Okay. Our test statistic for p-values is p hat minus p naught over the square root of p naught times 1 minus p naught over n. The p-value is an area under the standard normal curve. The area depends on the type of test determined by the alternate hypothesis. Again, this is nothing new. The p-value is the area for a left-tailed test to the left of our test statistic. If we have a right-tailed test where we think our proportion is higher than the null, then it's a right-tailed test, and it's to the right of z, the area. And if it's a two-tailed test where we think our sample proportion is not equal to the null, then it's the sum of the areas in both tails. So why don't you try this problem? Hit pause and try this problem and see if you can work through it. Then hit play and see how you do. All right. Education specialists in studying attitudes of teachers about the use of virtual reality in the classroom. She samples 500 teachers and finds that 471 of them believe that the virtual reality would have a positive effect. Can she conclude that the proportion of teachers who believe it will have a positive effect is greater than 90%? Use the alpha equals 0.05 level of significance. We have a simple random sample. We have a teacher population. We sampled 500 teachers. 20 times this would be 10,000. We can assume pretty easily that there's more than 10,000 teachers in our population. N times P naught, 90%. N is 500 times P naught. 0.9 is 450. That's greater than or equal to 10. N times 1 minus P naught is 50, which is still greater than or equal to 10. So we can, the assumptions are met. Our hypothesis is that the proportion is 90%, and our alternative hypothesis is that it's greater than 90%. Can she conclude the proportion of teachers who believe it will have a positive effect is greater than 90%? So that's our alternative hypothesis. Now we have everything we need to calculate our test statistic. Oh, did I lie there or what? We did not calculate 471 out of 500 our p hat, or the sample proportion. Now we have everything, my bad. P hat minus p naught over the square root of p naught, 1 minus p naught over n, and we get a calculation of 3.13. If we look in, we can see this is a right-tailed test. So if we look at 3.13, remember the value in that chart, A2, is the area to the left. So when you look at 3.13, you will find in the table at 3.13, you will find 0.9991, I guess. I think that's what it should be. And 1 minus that will give us the area to the right. So remember, table A2 gives us the area to the left. So when you look at 3.13 on the table, you will find that 0.9991. Subtracting that from 1, we get to 0.009. Since the p-value, which is 0.0009, is less than 0.05, this means we have what? It's like 0.09% of, and we're looking for values that are 5% or greater. So since the probability is less than 0.5, we reject the null hypothesis at the 0.05 level, because it's very rare that we'd have a sample in this area. We conclude that more than 90% of the teachers believe that virtual reality will have a positive effect on education. Again, in this section of 8.4, you've got great technology pieces that you may use on the test. This is for the TI-84. It's going to go through the exact examples we've just gone through, showing you how to set them, also how you can Excel, etc. All right, so let's try one more problem. Again, hit pause and see if you can do this problem on your own. The Pew Research Center reported that only 15% of 18 to 24-year-olds read a daily newspaper. The publisher of the local newspaper wants to know whether the percentage of newspaper readers among students at a nearby large university differs from the percentage in general. So this is just saying it doesn't equal the null hypothesis, so we have a two-tailed test. She surveys a simple random sample of 200 students at the university and finds 40 of them, or 20%, read a newspaper each day. Can she conclude that the proportion of students who read a daily newspaper differs from 0.15, and again we're going to use the 0.05 level of significance. Again, we check our assumptions. This says we skip assumptions. Oh, it tells you to skip assumptions. Sorry, I just said that. Maybe the example did that as well. My bad. Our null hypothesis is that the population proportion is 0.15, and our alternative is that it's different from that. Again, a two-tailed test. So now we have to do our sample proportion. Our p hat, 40 out of 200 was 0.20. It actually gave you that value there as well. Now we can calculate our test statistic, and we get 1.980. Again, we look in table A2. Now here, remember that we're looking at 1.980. We're going to subtract that from 1. This is a two-tailed test, but we can use the upper side, 1.980, or you could use the negative 1.980 to see the exact area. But if you use the 1.980, you're going to get a value, subtract that from 1, and you're going to get 0.0239, and because it's a two-tailed test, we have to multiply this by 2, so the total area is 0.0478. This is still less. It's very close. It's very close, and this is one of the things we talked about in the last section, why it's a good idea to report the p-values and the critical values that you get. Okay, so the p-value is less than 0.05. It's very close, and so we reject the null at the 0.05 level, and we conclude that the percent of students who read a daily newspaper is different than the 15%. So our critical value, the test statistic, is still p hat minus p naught over p naught times 1 minus p naught over n. Excuse me. And again, here we're looking to see not so much the area, but when we calculate the critical value, if it's a left tail, it's the negative z value, right? And we're trying to see if our statistic is inside one of the shaded tails, any of them, okay? So if it's a left tail test, it would be less than the critical value. If it's a right tail, it would be greater than the critical value. And if it's a two-tailed, it would either be less than the critical value divided by 2 or greater than the critical value divided by 2 on the positive side. So let's look at this. Again, this should be getting a little more familiar now. We're working through these type of problems in a very similar fashion, just some minor tweaks to the formulas. So if you want, hit pause and try this one. A nationwide survey of working adults indicates that only 50% of them are satisfied with their jobs. The president of a large company believes that more than 50% of the employees at his company are satisfied. He surveys a random sample of 100 employees, and 54 of them report that they are satisfied with their jobs. Can he conclude that more than 50% of employees at the company are satisfied with their jobs? Use the alpha equals 0.05 level of significance. Okay, it's a large company, and we sample 100 employees, and so we get n times p naught is 100 times 0.05 is 50, n times 1 minus p naught is 50. Both of these are greater than or equal to 10, so we can move forward. Our null hypothesis is that 50% of the employees are satisfied, and our alternative is greater than 50%. Okay. Our p hat, 54 out of 100 is our p hat, or our sample proportion, 0.54. We can now calculate the test statistic, p hat minus p naught, etc., and we get 0.80. This is a right-tailed test. Remember that the critical value for a 0.05, when we're trying to find the critical value, this is all related to the alpha equals 0.05 level. Okay, since we're talking about a right-tailed test, that means that 0.05 out of 1 is in the right end tail. That means that to the left of that marker is 0.9500. Okay, if you look at table 8.3 at the bottom, it gives you the z-score, or the critical values, for each of the alpha levels listed at the top. I've also included this as a formula sheet for all the tests that you can use this. But you could also go into table A2, find the z-score that equals 0.9500, 0.9500, and you would find this 1.645 z-score as well, which is the critical value. Okay, so there's multiple ways, and I wanted just to tell you that, not to confuse you, but to see how these are linked very logically, etc. And if you use them more, you would see that. Okay, when we look at the normal graph, we can see that 0.8 is not in the critical area, or the critical region. It's not to the right of 1.645, so we do not reject the null hypothesis. And what do we say? There is not enough evidence to conclude that the company president is correct in his beliefs that the proportion of employees who are satisfied with their jobs is greater than 0.5, or 50%. Okay. Try another. Again, hit pause, and this one tells you to skip the assumptions, just jump right into the hypothesis and calculate and see how you do. A Gallup poll sampled 1,000 adults in the United States. Of these, 770 said they enjoyed situations in which they competed with other people. Can you conclude that less than 80% of U.S. adults like to compete? Use the significance level at A equals 0.05. Okay. Our null hypothesis, 770 out of 1,000 adults. All right, so our null hypothesis is that 80% of U.S. adults like to compete. Our alternative is that the proportion is less than 80%. Okay. Our actual proportion here, 770 over 1,000. That's our sample proportion. Our p hat value is 0.77. We can then calculate our test statistic, and we get negative 2.372. From this, we can look at our critical value for 0.05. 0.05, the value is 1.645, but since we're on the left side of the screen, it's going to be negative 0.165 because it's a left-tailed. Okay. And we can see that negative 2.362 is less than 1.645. Again, I like to visually graph it. I didn't do it this time. I like to graph that normal curve, draw a line for negative 1.645, and then all the area to the left is the critical region. I can see easily that visually when I draw the normal curve, that is to the left of that and it's in the critical region, so we would reject the null hypothesis. We conclude that the percent of adults who enjoy competing with others is less than 80%. So these are the things we covered in section 8.4. We've gone through all of these, both doing a hypothesis test about a population proportion, understanding the different assumptions for hypothesis tests for proportion, and how to conduct those tests using the p-value or the critical value method. This is our final section, and this is a really quickie about looking at hypothesis tests. Specifically, we're first looking to figure out which type of tests we're using. If it's a population mean, we have two different ways of going about that using the z-score or the t-score. If it's a population proportion, we also have two different ways, but we can use either of those ways. With the population mean, there's a very specific kind of logic to which method you use, and that's given by this table here. So the first question you're asked, am I looking for a mean or am I looking for a proportion? If I'm looking for a mean, then I use this table. If I look for a proportion, I can use either of the methods. All right, so the first question I ask is, do I know the standard deviation of the population? If I do, then I ask, is the sample greater than 30? If it is, I use the z method. If the sample is less than 30, I ask, is the population approximately normal? If it is, I can still use the z method. If it's not explicit that it is, then I need to consult a statistician. Going back to the start, maybe we don't know the standard deviation of the population, which is actually quite common. We still then ask again, is the sample size greater than 30? If it is, we use the t method. If it is not, we ask, is the population approximately normal? If it is, if it's explicitly is, we use the t method. If not, again, we consult a statistician. A simple random sample of 150 cars undergoing emissions testing, 23 failed the test. Can you conclude that the proportion of cars that failed the test is less than 20%? So you can actually do this problem. We are trying to find a proportion, so we do not need this table. It's a proportion test. We can use a p-level or a critical value test. And if we do this one, we would find that we do not reject the null hypothesis. The second one, B here, a sample size of 15, has a sample mean of 27.72. The population is approximately normal. Can you conclude that the population differs at the 0.01 significance level? So do we know the standard deviation? I don't see a standard deviation in here, so I would say no. Is n greater than 30? No. Is the population approximately normal? We do have a yes, and so we would use the t method, and we would find out that we, in this case, would indeed reject the null hypothesis. And you can try to go through those and do all the calculations. We just did several examples for the population proportion today in this lecture, and then for the mean we did in the previous lecture. Okay. Again, we have two more of these. Try these. Sample of 300 electric components, 35 were defective. 10% of the components of this type are defective. Again, we're looking at a population proportion. We do not use the chart, and in this case, we wouldn't reject. We have a sample mean of 38, a sample size of 65. We know the standard deviation, so again, yes, we know the sample size is greater than 30. We would use a z method, find the z-score, and in this case, we would reject the null hypothesis. So that's the end of the course. This is the final note, and so that's all, folks. I hope this lecture video has helped you, and as in any sport, it's the practice that's king. So make sure you're practicing these as much as possible.